partially completed numerical yesterday, and for this numerical, for this BJT amplifier, the capacitor, the bypass capacitor was absent, and we were supposed to find the DC parameters, IPQ, ICQ, the small signal parameters, RPi and GM, and the cutoff frequency due to the coupling capacitors CC1 and CC2. And I think also we determine FL, the overall cutoff frequency. So these were the parameters given to us: R1, R2, R3, RE, RC, then CC1, CC2, RSig, and RL. And BJT parameter was beta equal to 200. So let's revise what we have done so far. So from this analysis, we have got VTH equal to 1 volt, RTH is 1.98 kilo ohms. I hope that you all have verified this. Then we have IBQ is equal to 13.58 microamperes. ICQ is equal to 2.72 milliamperes. Then we have small signal parameters. RPi was 1.91 kilo ohms. GM was 104.61 milliampere per volt. Then we wanted to find out FL of CC1 and CC2. So we have drawn the low frequency small signal equivalent circuit. And after that, individually for FL of CC1, we have done the analysis and we found out that FL of CC1 value, after doing the analysis, is coming out to be 1.761 hertz. And RI value was 1.816 kilo ohms in the process. So I hope that you all have got this value also for calculations, right? Then we went on to calculate the FL of CC2, the lower cutoff frequency due to CC2, and it came out to be 11.287 hertz, right? And finally, we found out the value of FL, the lower cutoff frequency, which was the higher maximum value compared to that FL of CC1 and FL of CC2. So it was supposed to be 11.287. So that is what we have left in the last lecture. So today we are going to start with the calculation of AV mid, the midband voltage gain. So let me cut this part. Actually, I've already prepared that on the other one. Yeah. So let's start with today's. Okay. So today we will continue this numerical and calculate AV mid. Okay. We'll calculate AV mid, and here we have common emitter amplifier with emitter degeneration. So there is this concept of emitter degeneration. What does the emitter degeneration mean? Emitter degeneration means that your emitter terminal is not bypassed via the coupling capacitor. So CE is absent. So if your bypass capacitor CE is absent, then RE won't be sorted to ground. So RE will be connected as it is, right? And that is what exactly we mean by common emitter amplifier with emitter degeneration. And if we have a simple amplifier, right? If you have a simple amplifier which is something like this, which looks something like this, let me draw that and show it to you. So you have a voltage divider bias over here. You have R1, R2, RE. Okay. And then you have let's say you have, this is VS, this is VCC, R1, this is R2, R1, R2, this is CC1, and we have, this is V out. Okay, CC2, RC, and RE. So this amplifier, BJT amplifier, which we have drawn, doesn't include RSig, and it doesn't have a load. Okay, so this small signal mid-frequency equivalent circuit over here, which we have drawn, corresponds to this amplifier, and its gain, it's written by minus RC divided by 1 upon GM plus RE, right? So this is what the expression was for a common emitter amplifier with emitter degeneration, right? I'm not going to derive this. I think this was done in the common emitter amplifier itself for emitter degeneration. So that's the formula. Now what we have to do is, according to our circuit, we have to tune this. Okay. So what do we have earlier in in this circuit? We have RL extra. So we have this RL which is extra over here. Okay. So this is extra, and we have R6 into picture which is extra. So how do we proceed it? How do we write the formula? So if I write the formula as AV mid is equal to what should be the formula? Voltage gain V out divided by Vs. Fine. And V out and Vs, intermediate, we can define a voltage V in over here. Okay. If we define a voltage V in, that will make the analysis much simpler. So this is actually ground. Okay. So V in is the voltage across R1 and R2. Right. Now, how do we proceed forward? We can write the formula as V out divided by V in into V in divided by Vs. Agree? Any doubt over here? So we know how to write the formula for V out upon V in, right? So that is what we have done over here, right? V out upon Vs in this case. If we assume that there is no RC, right? So we have to add a RL over here, and that RL is parallel to RC. That's the only difference. Rest the formula will remain the same. So we can easily write this V out upon V in for this network over here. So can anyone help me out in writing this? What is V out upon V in for this? What will be V out upon V in for this circuit over here? It will be minus RC parallel to RL minus RC parallel to RL divided by 1 upon GM plus RE. Okay, so that's the formula. Minus RC parallel to RL divided by 1 upon GM plus RE. Correct. Now, next, we have to find out the value of V in upon Vs. So how do we do that? Anyone? Any ideas? How do we calculate V in upon Vs? We have done this before in the last lecture itself. So V in upon Vs, I mean, we can write it in this form. So if I draw the circuit again over here, I mean this part, right? This part of the circuit over here. So what I can take from here is something like this. So what I can do is I have to consider V in. So this is V in, right? So let me draw it over here. Let me redraw this part over here again. So what I will do is I'll cut this part and I'll redraw it once more time so that the analysis becomes simpler. Okay, only thing is that. Okay, I'll copy this and I'll paste it below so that the analysis becomes simpler. Okay, so let me add it over here again. Okay, fine. Now how do we analyze this part? Anyone has any ideas? Yeah. So how do we analyze this part? This part is gone because the impedance seen by the if you see the impedance by the current source, it's infinite, right? So here again, the impedance seen by the current source will be infinite over here. For if you consider V in upon Vs. Okay. So now how we will proceed ahead? Anyone? Come on, yesterday we have discussed this. If I have to write, I mean this is V in, right? So if I have to draw the same circuit like this. So this is my Vs. Okay. This is my ground. This is RSEG, and let's consider this an entire system itself. Okay, so this is an entire system itself. Let's consider that. Okay, this is a system, and we are supposed to find Ri for that system, and the voltage across this is V in. by, sorry, V in. So how can we write? I hope I am audible.
Yes,
Hello,
sir.
can someone else?
Yes, sir, you are
Okay,
audible.
if there is disturbance in the voice, immediately let me know. Huh? I will repeat that one. Okay.
Sure, sir.
So now let me continue further. So what I'm going to do now is, this is a simple voltage division, right? I can draw the following circuit as follows also. So here I can represent Ri in this form. So let's say we have a resistance Ri over here. So how can I write V in and Vs? So by voltage division rule, right? So V in will be equal to Ri divided by Ri plus R6, correct? Into, this will be into Vs, and this is possible by voltage division rule. By voltage division rule, this is what we get. So we can have V in upon Vs as Ri upon Ri plus R6. So basically we have to find the Ri over here. This is the system which we are talking about. Okay, here it is. This is the system which we are talking about. So here we have to find the value of Ri. So anyone can help me out in this? How will I write Ri? Yesterday we have discussed this fact. So Ri will be equal to, anyone? Ri will be equal to, see, R pi and Re are in parallel, are in series, right? And that
Sir,
combination which is parallel
R
with
pi
R1
plus
parallel to
Re
R2.
in parallel with R1 plus R2, R1 R2.
If I write that, you mean to say like this, right? R1 parallel to R2, correct?
Yes,
Parallel
sir.
to R pi plus Re, right?
Yes, sir.
But this is wrong. Now why this is wrong is, listen carefully now. This base terminal, right? So R1, R2, R pi are associated with base terminal. So the base current will be, this is the base current which flows, and here there is an emitter terminal. So here emitter current flows, right? So can you tell me what's the relation between emitter current and base current? Are they same?
No, sir.
They are not same, no? So if I want to represent IE in terms of IB, so what I have to do? If I have to convert this into IB, what I have to do? Multiply this
Beta
by
plus 1 times
1
IB.
plus beta. Correct. This will become this. Now can you tell me the related form?
Sir, we'll write Re as beta plus 1 times.
So this is wrong. So what you
Yes.
will write? Ri will be equal to R1 parallel to R2 parallel to R pi plus 1 plus beta times Re. So this is the huge value of Ri. Are you getting the point? If you don't include your bypass capacitor, this is how complex it becomes. Now what you have to do is, Ri we have to calculate it individually. I don't know whether we have done that before. And then we have to calculate after Ri. When you calculate Ri, then you have to calculate V in upon Vs, which is equal to Ri divided by Ri plus R6. Okay, so that's how the that's what the plan is. So let's see whether we have calculated this entire fraction over here, Ri parallel to that. I guess we have done that over here, right? R1 parallel to R2 parallel to R pi plus 1 plus beta time Re, correct? So it's coming out to be 1.816. So someone please confirm 1.816. 1.816 is the value of Ri. 1.8. I am not sure. You please confirm. One of you please confirm. 1.816 kilo ohms divided by So if you are getting any other answer, please report it to me. What is R sig value? R sig value is 100. Okay, so this number will come out to be, if you calculate, it will come out to be very close to 1. It is 0.947. So that's the value of V in upon Vs. That's the value of V in upon Vs. Now what else we have to calculate? We have to calculate V out upon V in also. So let's calculate V out upon V in. So V out upon V in. So RC parallel to RL. I guess we have calculated RC parallel to RL before also. Let me confirm. Actually here is some mistake. It should be plus. It shouldn't be. We have not calculated RC parallel to RL. So let's calculate that. RC parallel to RL. Oh, sorry for that. Okay, so let us calculate the value of RC parallel to RL. What is RC value? How much is RC value over here? 2K, right? So RC value is 2K, RL value is 1K. Then the GM value is how much? 104.6 milli, and RE value is how much? 100. Okay, so please calculate it. You'll get it as 0.66K, 2K parallel to 1K, divided by 1 upon GM. It will be 1 divided by 104.61 milliampere. That will be 9.56. Please confirm the answers, okay? Plus 100. Okay, so value is coming out to be how much now? Divide this number, divide this fraction, and let me know. And it's minus, okay? Minus. How much is this? Can anyone let me know this? Is it 6.078? One of you do this in calculator.
So 6.024.
And please okay, fine. 6.0. It is 0.66 divided by 9.56 plus 100. Yeah, it is into 24. Fine. So that's the value of V out upon V in. So now if I have to calculate now next AV, total AV mid. So how to do that? My AV mid will be minus 6.024 into V in upon Vs. What is V in upon Vs over here? 0.947. Okay. So 0.947. So please multiply the two. So how much is this? Anyone? Is it coming out to be around minus 5.7?
Yes, sir.
Okay, minus 5.705. So that's the value of AV mid. Now AV mid has to be calculated in dB. AV mid have to be calculated in dB. So what will I do? How will I proceed forward now? What's the formula?
So 20 log AV mid.
Yes. So AV mid dB will be 20 log to the base 10 mod of AV mid, which is 5.705. And this is, how much is this value? (20 log to the base 10 of answer). Is it coming out to be 15? 15.12 dB. Please confirm this.
Yes, sir.
Okay, very good. So we have finally found out the value of AV mid. It's coming out to be 15.12 dB. Okay, and now what is next left? We have to plot the frequency response, and we know how to do that. Plotting of frequency response is quite simple now. Let me see which step was this. Step number 8. So now step number 8 we have to do now. Last step is plot the frequency response. Okay, so let's plot the frequency response together. So here we have y-axis, x-axis. Y-axis, what you will write? AV mid in dB, and x-axis you will write frequency, which is log scale, basically, right? And how will the plot look like? Agree? So this is the low cutoff frequency. And how will you calculate FL from here? This value is how much? AV mid. AV mid maximum value is how much? 15.12. So this value over here is 15.12 dB. When you do in your labs, experiment number 1 is about this only, calculating the frequency response, plotting the frequency response. So how will you calculate it? Go 3 dB down. Go 3 dB down. This is 3 dB down. And mark the frequency on the x-axis. And this will be your FL. Okay. So this is your FL. And what is the value of FL which we got? 11.28 Hertz. And this completes the frequency response plot. Okay. So the main values of this numerical were calculate the midband voltage gain, that is 15.12 dB, and calculate the cutoff frequency of the amplifier, which is 11.28. So they might ask you only these two things, but we have to calculate all the things which we have said before. Understood? So here we have completed this numerical. If you have any doubt, you can ask. If you have any doubts, you can ask. Or else we will proceed to the next numerical. Everything is clear about this? Everyone is clear?
Yes, sir.
Yes, sir.
Okay. So let's move on to the last numerical of BJT amplifier. Then we'll move on to next time MOSFET amplifier. Okay. So low frequency part will be completed. So for BJT, next time we'll take 2 lectures for MOSFET, and 1 lecture or 2 lectures for MOSFET low frequency. Then we'll move on to high frequency. Okay, so high frequency will take again 3 or 4 lectures, and then we'll wind up this first module. Okay, fine. So let's begin. So this is analog electronic circuits 6.2. And today's date is 21st. Okay, fine. So let's start with another numerical. I will be drawing a diagram in front of y'all. Y'all have to identify which is the circuit which we have. Okay, so please draw it along with me. So here we have a resistor. We have R1 over here. Here we have R2. Then the collector terminal is directly connected to VCC. Okay, here we have plus VCC. Then the output is taken from the emitter terminal. And then we have a RL, load RL. And here we take the output from. This is again a BJT amplifier, but which configuration it is? Can anyone tell? Looking over here, so we have RSIG also, and we have coupling capacitor over here, CC1. This is RSIG, and here we have VS. Plus minus VS. This is connected to the ground. R1, R2, and RE. This is CC2. So write down the values of the R1 and R2. R1 value, first of all, VCC value is plus 12. Okay. R1 value is 50K. R2 value is 25K. RE value is 5 kilo ohms. RL is 2 kilo ohms. Then we have CC2, which is 0.4 microfarad. CC1, which is 0.3 microfarad. RSIG is 1 kilo ohm. Okay, and your input is AC, small AC quantity, and output is also AC. And this is DC. Okay, now can you identify which configuration it is? Can someone identify how many configurations are there for BJT? Common emitter, common base, and common collector. Now tell me which configuration it is.
Sir, common emitter.
No, it is not common emitter.
Sir, common base.
Neither common base. You all don't know only what is common emitter, common base. So only option left is common collector. Input applied at base terminal, and output is sensed at emitter. So you all know the definition of common emitter, common base, and common collector. It's not because emitter is common terminal. No, emitter is common terminal in the AC analysis, in the small signal equivalent circuit. In the common base terminal is common in the AC. AC ground is common, not the DC ground. Understand that. Here it is, here if you say again a common emitter, but no, it depends upon where you apply the input and where you take the output from. So if in an amplifier input is applied to the base terminal and the output is taken from the emitter terminal, then it's a common collector amplifier. Are you understanding the point? Okay. And if the output was taken at the collector terminal, this becomes a common emitter, right? And if the input is applied to the emitter and output is taken from the collector, then it's called a common base configuration. So please understand the difference. Okay, this is a very, very important question. So the above configuration is common collector amplifier. So you have to be very, very careful and vigilant. It looks like a common emitter, but it's not common emitter. The collector terminal is directly tied to the VCC. Okay. So what they are asking us to find out, they are asking us now to find number one. I'm not writing the statements. Statements you will get it from the module 1 questions. So they are asking us to find FL, overall cutoff frequency, and second is AV mid. That's it. No need to plot the frequency response. They are asking us two things only, FL and AV mid. Okay. So everyone has understood why it is a common collector amplifier. If you have any doubt, you can ask. Now, I will give you around 2 minutes to calculate the value of VTH and RTH for this network. Okay, RC is not present. How will you proceed? So be careful. I will solve it for you all, no problem. But I will require you all also to try it at your end, because this will be easy now for you all. But remember, RC is not there in the circuit. So first will be the DC analysis, or we can write calculation of IBQ and ICQ. Correct? So let's start. What will you do? What you have to draw the AC equivalent, I mean the DC equivalent circuit, right? So how will the DC equivalent circuit look like? Without the capacitors. This is your VCC. R1, R2 and RE. Okay, this is your base, collector and emitter. Now how will you proceed forward? Will you use the same technique? VTH is equal to R2 upon R1 plus R2 into VCC. RTH is R1 parallel to R2. Yes or no? Because normally what you do, you apply Thevenin's equivalent next. For this network, how do you analyze it? You apply Thevenin's equivalent and then how will you convert it? This way, right? I hope that you all are aware of this. You apply the Thevenin's equivalent at the base terminal and we get this VTH, RTH, and that will be connected to VCC. Only difference being, earlier we had a resistor RC, but here it is directly connected to the collector terminal, is directly connected to the VCC. So here is my emitter and base. And now how will you proceed? This is my VBE. Okay, this is RE. So what do? You apply the KVL to the input loop and then you find out the value, right? So for this network, your VTH will be same as we have found out earlier. So VTH is R2 divided by R1 plus R2 into VCC. Okay, so let us check out the values again. R1 value is 50 kilo ohms, R2 value is 25 kilo ohms, VCC is 12, RSIG is 1 kilo ohms, CC1 is 0.3 microfarad, CC2 is 0.4 microfarad, RE is 5 kilo ohms and RL is 2 kilo ohms. And here the beta value we have not written. Please write down the beta value. The BJT parameter beta value is 100. If in the exam they don't give you the beta value, please ask for. And if they say you can take any value, you can assume there, you have to write there, we assume the beta value to be 100 or safely 200. So if they don't give, specify, then you can safely take 100 or 200. If they specify, take that particular value only. So let's continue our discussion now. So R2 divided by R1 plus R2. Now please calculate it. Calculate this value. It will be 25K. Just keep on verifying it. Divided by 25K plus 50K into 12. So VTH comes out to be, if you solve it, you will get it as 4 volt. I hope you all are also getting it as 4 volt. Then next we have is RTH. This is pretty straightforward. R1 parallel to R2, which is 50K parallel to 25K. So this you also solve, you will get it as 16.67 kilo ohms. So we have calculated RTH and VTH. Next we have to calculate IBQ. So will the IBQ formula remain same? Yes, because IBQ is derived by applying the KVL to the base emitter loop, and base emitter loop is same, right? Only the output loop is affected. Okay, RC is not there, but the IBQ formula also will remain the same expression. So IBQ will be given by VTH minus VBE divided by RTH plus 1 plus beta times RE. Now they have not given the value of VBE, so you have to assume VBE to be equal to 0.7 volt. You have to write that. Whatever is not given, you have to assume that value. So your value of IBQ will be VTH is 4 volt, 4 minus 0.7 divided by RTH plus 1 plus. So RTH is 16.67 kilo ohms plus beta is 100. So 101 into RE. RE value is 5K. So please calculate this, solve it in the calculator. You will get it as 6.325. Please verify these numbers. If you get anything different, please do notify. Okay. So this is calculated. What next we have to calculate? ICQ. So ICQ is beta times IBQ, which is 100 into 6.325 microamperes. So this will be 0.6325 milliamperes. Please write the units carefully. IBQ will always be in microamperes and ICQ will always be in milliamperes. ICQ. Okay, this much completed, everyone. Please, one of you please confirm this. One of you please confirm.
Yes, sir.
Okay, fine. So good. So the DC analysis part and calculation of IBQ and ICQ is completed. Next, what do we find out? What do we normally find out next? Calculate small signal parameters. Okay, so calculate small signal parameters. So what are the small signal parameters? RPi, GM and RO, which make up the small signal model. So let's start. So what was the formula for RPi? Anyone? What was the formula? Beta VT divided by ICQ. By now you should remember. And what's the value of VT? VT always you have to take it as 26 millivolt unless specified. So it will be beta is 100 into 26 millivolt divided by ICQ, which is 0.6325 milliamperes. So over here 10 raised to minus t, 10 raised to minus t will get cancelled, and you will get, if you calculate it in your calculator, 4.11 kilo ohms. So please confirm this number. Next we'll calculate GM, which is ICQ divided by VT, which will be 0.6325 into 10 raised to minus 3 divided by 26 millivolt. So again your 10 raised to minus 3 will get cancelled, and your GM value, how much is GM value? Someone please tell me the GM value. 0.6325 divided by 26. Is it 24? 24.33. Unit is milliampere per volt. So that's the value of GM. Fine. How will you calculate the value of RO? It can be infinite.
Can you repeat? Your voice was breaking.
Now it is fine. RO has to be infinite.
Yes, sir.
Yeah. So RO has to be infinite since VA, early voltage, is not given. So we have calculated RPi, GM and RO. Right. What is the next thing we do? Anyone? So all of you must get this value of RPi, 4.11. GM value is 24.33. Right. And what is next? RO is infinite. Now what do we do next? We'll draw the low frequency AC equivalent circuit. Right. So next we draw low frequency AC equivalent circuit. Or low frequency small signal equivalent circuit, one and the same. So we have to draw this now. So we will require the diagram now. I will draw that diagram in short over here very quickly. So we have this network. Collector was connected to the, creating the diagram which we had. Okay. Here we had a VS, right? This is VS, R sig, CC1. This was the supply. R1, R2. This is RE. This is CC2. This is V out, and this is RL. So based on this, we have to draw the low frequency AC equivalent circuit. So first of all, we have to replace, what we have to do? We have to replace the transistor by its hybrid pi model. So this is base, this is collector, and this is emitter. So everyone pay attention how to draw it. So first of all, you have to draw the hybrid pi model. So in the hybrid pi model, what do we have? We have the base terminal over here. Then we have the collector, and over here we have the emitter terminal. Okay, so between the base and emitter, what do we have? We have R pi, right? We have R pi resistance. Between collector and emitter, what do we have? We have a current source, voltage dependent current source, whose value is given by Gm into V pi. Where is V pi? This is V pi. Okay, so this is your hybrid pi model. That means you have replaced your transistor with a linearized hybrid pi model. Now, how do we proceed? How do we proceed? You know that your in the AC equivalent circuit, your VCC will be grounded. Okay, VCC will be grounded. So you will have R1 parallel to R2. Okay, on this side, we will have R1 parallel to R2 over here. Okay, so this will be R1 parallel to R2. What else we will have? We will have a capacitor also as it is. And then we will have R sig. I'm just drawing this part of the circuit as it is. So this is my VS. This is R sig. This is CC1. Now, can you tell me where will the collector terminal go? Anyone? Quickly tell me where will the emitter terminal go? Yeah, come on. Look
So
at the
emitter
diagram and
will
tell
lead
me.
to output.
No, where it is emitter output?
So
Is
the output
emitter
is
connect
across the emitter, right?
Emitter is connected to output. Collector. Sorry, where will the collector go?
So ground.
Yes. Collector will go to ground. Emitter will definitely go to the output. But first we have to connect it to resistor RE. Then we have a capacitor CC2. Then we have a resistor RL. Then across the resistor RL we have the output. Yeah, correct. Please draw this low frequency AC equivalent circuit in your books. Okay, so based on this circuit now, small signal low frequency equivalent circuit, we will calculate FL of CC1 and FL of CC2. Okay, ready? Okay. So let's first calculate FL of CC1. Okay. I'll start from here. Let me just yeah, I guess this much is fine. So let me add that small single equivalent circuit over here. Yeah, fine. So next step is calculation of FL of CC1. So how do we calculate it? What is the step? We have to sort circuit VS source and CC1. Okay, we have to sort VS source and CC1. So sorry, CC2, not CC1, CC2. So how do we do it? We will take this and short circuit the VS source, and then at the emitter side over here, we will again sort this. Okay, now calculate the circuit now. Is this looking quite familiar? What we have to do, right? We have done that many times. Let me draw it one more time over here. So we have a, I mean, we have a system in place, right? Where when we have a voltage source, and then we have to calculate, this is a system which we are talking about. What is the system which we're talking about? Here it is. So this is a system, and we have to calculate, sorry for that, actually, yeah. We have to calculate Ri for that system. Ri. Right. Now, how do we calculate Ri? Obviously, the impedance which is offered by this current source will be infinite. Correct? So here this will be infinite. So from the collector, from the collector to emitter terminal, we have open circuit only directly. Now, how do we find it? How do we find Ri? So what is the formula for FL of CC1? It is 1 upon 2 pi R equivalent into CC1, where what is R equivalent? R sig plus Ri, and we are here to find out the value of Ri. So anyone, come on, we have done that many times now. Please tell fast. The current flowing over here is IB. Remember, the current flowing over here is IE. Now tell me the formula Ri. Come on, quickly now. It should be a practice now to you. Anyone? Ri,
Sir,
I mean expression.
sir, R pi plus beta
R1
plus 1 into RE in parallel with R1, R2.
RL will not come.
Yes, sir, I will also come.
Okay. So R1 parallel to R2 parallel to R pi plus 1 plus beta times RE parallel to RL. Just we have extended the concept. Okay. Because the current flowing through base terminal is IB and current flowing through emitter terminal is IE. And how they are related? IE is 1 plus beta times IB. Okay, so that's why this 1 plus beta times term is coming. Now you have to calculate this and then let me know how much is the answer. So according to my calculations, R1 plus R2 is 16.67 K. R pi value is 4.11 K. 1 plus beta is 101. RE parallel to RL. It's basically how much it is? RE parallel parallel to RL. It's 5K parallel to 2K. So that's 1.428K. So if you calculate this entirely in calculator, you will get close to 14.98. So please check this answer. Right now I'm moving ahead because we have to complete this numerical now. And finally, if you substitute this answers over here, FL of CC1 will be equal to 1 upon 2 pi into 14.98 K plus R sig. R sig value is 1K into CC1. CC1 value is how much? 0.3 into 0.3 microfarad. So microfarad is 10 raised to minus 6. So FL of CC1 is coming out to be 33 something, 33 hertz. It's coming out to be 33.2 hertz. So please check out this answer. Okay, it's coming out to be 33.2 hertz. Fine, everyone. Next is I'll calculate F. Next I have to calculate is calculation of calculation of FL of CC2. Okay, so for calculation of FL of CC2, let me have to copy this diagram again. What will happen is after 2 minutes or 3 minutes, please leave the meeting. You have your next lecture at 3:15, right? I will continue the recording and complete the numerical. Then later on you can access the recording, okay? So in 2 or 3 minutes time, please leave the meeting. Let me complete this part. I will let you know quickly. Let me quickly complete this. So you have here for FL of CC2, you have to short circuit VS and CC1. Okay, so here I'll replace the CC1 by a short and VS voltage source also short. Okay. Okay, fine. So how will you proceed now? How will you proceed? So here we have a system. This everyone, those who wishes to leave can leave now because we have a next lecture. This is RL. Okay, and here we have a system in place. Here it is. This is the system. This is C2 and this is RL, and we have a V out over here. So how we have to calculate this? For that system which we are talking about this system over here which we have. Fine. And for this system, we have to calculate the value of RO. I'll request everyone now कि y'all can leave the meeting if you want. I will share you the recording. I will continue to record for around 15 minutes more till I complete the numerical. Please do not continue joining here. Y'all can leave the meeting exactly at 3:15 also. So no problem with that. Okay? No, not at all a problem. So here we have to calculate RO. So I'll gently request you all to leave the meeting by 3:15. I'll continue the recording further. So the current flowing through the emitter is given by 1 plus beta times IB. Let me write small IB. And if I want to write IB in terms of IE, how can I write it? IB is IE divided by 1 plus beta. Okay, IB is IE divided by 1 plus beta. That is what exactly we will be doing over here. Over here, the impedance offered by the current source will be infinite again. So impedance offered by this current source will be infinite. So this terminal will be open circuited. Okay, so here it will be open circuited. Again, I request you all to please leave by 3:15. I'll continue with the recording and complete it. You can watch it later. Okay, fine. So now, if I want to write, now see carefully, we are going from emitter to base. So all the current over here should be in the terms of, what? Should be in terms of emitter current now, not the base current. We are doing the other way around. So what will be the value? RO. So RO will be given by RE, then everything else, it will be in, RE parallel to R pi plus, R pi plus R1 parallel to R2 parallel to R sig, right? If I write it like this, it will be RE parallel to R pi plus R1 parallel to R2 parallel to R sig. Will it work? Well, no, this is wrong, because current flowing through emitter is IE, and current flowing through R pi, R1, R2 and R sig is IB. So how will you convert your emitter current into your, base current like this, in this format, right? So base current can be written as IE divided by 1 plus beta, right? So this entire thing will be divided by 1 plus beta. So that's the formula for the RO, expression for RO, right? And then we have, then it's very simple. R equivalent will be, what will be R equivalent? RO plus RL. Okay, R equivalent will be RO plus RL. Those who have not left the meeting, please leave the meeting now. And FL of CC2 will be equal to 1 upon 2 pi R equivalent into CC2. Fine with this? So let us complete it, let us complete this further. So here you will have the various values are given to you. So beta, this will be around 101. R1 parallel to R2 is 16.67 K. R sig value is 1 K. R pi value is 4.11. Okay, and RE value is 5K. So if you calculate it further, you will get RO equal to, you should get RO equal to 50.02, close to that. Similarly, R equivalent will be RO plus RL. So it will be 50.02 plus RL, and RL value is around 2K. Okay, so it will be 2.05. So we will substitute these values in FL of CC2. So here it will be, FL of CC2 is coming out to be 194.08 Hertz. So you all can check out this value. Those who have not left the meeting, please leave the meeting. You all have your next lecture now. I am continuing the recording and completing this numerical. So FL of CC2 is coming out to be 194.088 Hertz. Okay, and here we have to select the value of next is, let me go to the next part. So next comes the calculation of FL. So that's the sixth part over here. Calculation of lower cutoff frequency, FL. Now we know that FL will be the maximum out of FL of CC1 and FL of CC2, and how much is FL of CC1? That value is 33.2. And what is FL of CC2? 194.08. So you have to select 194.08 value. So that will be my lower cutoff frequency. So this is the lower cutoff frequency which we wanted. Okay, it will come after calculating all these stuff which we have discussed so far. Okay, fine. So further, if you want to enhance, further if you want to proceed, then next step is to calculate calculation of AV mid. Next is calculation of AV mid. So how will we proceed with the calculation of AV mid? Let me just go over here. So AV mid, for AV mid, the circuit will remain the same over here, but only thing is your capacitors will be replaced by a short circuit. Okay, so let me just copy this part. Okay, let me cut this part over here. Just a minute. You all have to draw it over again. For the first time, you can draw it once. Okay. So let me copy this and let me go down now, and I'll paste the circuit over here. And then from there, I will remove the, the capacitors. Capacitors are not present in the mid-frequency equivalent circuit. Okay, fine. This is what we get. Let me rub this out. So what's the difference between low frequency and mid frequency? In mid frequencies, capacitors are replaced by a short circuit. So capacitors will be replaced by a short circuit. So this becomes the mid frequency equivalent circuit, right? Now, I think you all might be already knowing about this common collector configuration. If I don't consider the load, let's say that here it is V out. Okay, let's for a moment consider that there is no load. Okay, RL is, and also RSig is not there. Let's just consider for a moment. We only have this amplifier. So let me draw it quickly. Of course, we have RL connected in this case, but let's consider for this case for once. If we have only this much is my common collector amplifier, right? So this is my common collector. And for common collector, the gain formula is well defined. The gain expression, okay, sorry, it is common collector amplifier. And for common collector amplifier, over here, if I want to write V out, let's say this is not Vs, this is V in. V out upon V in. Sorry for that. V out upon V in is actually well defined by the formula, which is very, very clear. So it is given by RE divided by 1 upon GM plus RE. So that's the formula which is well defined for a common collector amplifier. If you don't recollect this, you have to remember this formula. Okay, fine. So using this information further, now what we will do is we'll do the additions, right? So again, over here, what we will do is we can define this as input over here. Let me just take the color. So here we will define V in. Okay, so what is V out? AV mid will be V out upon Vs, which will be basically V out divided by V in into V in divided by Vs. Fine. V out upon V in, we know this is the formula. But in this formula, they have connected RL also, right? So if you have a RL over here, what we have to do, I will let you know. So if you have a RL connected over here, so let's say it will have a RL. How will it impact the formula? Wherever you see RE, RL will be in parallel. Okay. So over here, if you see, RL will be in parallel to that. So here we'll have RE parallel to RL, and here you will have RE parallel to RL. So V out upon V in formula is sorted out. We know what is V out upon V in, right? So let me write it again over here confidently, that V out upon V in is given by, there is no negative sign, a positive sign only. RE parallel to RL divided by, sorry, divided by 1 upon GM plus RE parallel to RL. You have to remember the basic formulas, or else we cannot sit and derive the formula for a voltage gain for a numerical. Okay, so you have to remember it like this and then do the additions. Only RL and RC is the extra part. So we have taken care of the V out upon V in. Now what about V in upon Vs? So for V in upon Vs, again we might have to, bifurcate the part of the circuit. So let me just do that. Okay, so I will copy the circuit again. What are we calculating? We are calculating V in divided by, okay, I have to slightly go down. Yeah. So let me pick up the circuit from here. And then I'll copy it so that I want to calculate. Yeah. So I will add the circuit over here now for calculation of V in divided by Vs. Fine. Now, if you look carefully into the circuit over here, what do we have? We have a current source. So current source impedance will be infinite. Okay. So this impedance over here, looking into the current source, will be infinite. So that is gone. Okay, that will be gone from the circuit. Now we have to determine, now the circuit will look something like this. Let me draw it. Okay, so equivalent form, if I want to represent this circuit, it will look something like this. So you will have a voltage source Vs, then we have a resistance R sig, and then we have a system in place. So that's my, okay, so that's my system, right? So from here we have to calculate R, here we have to calculate Ri of the system. Okay, if this is my system, we have to calculate Ri by looking into this. So this is my Ri. And now with a simple voltage division rule, and sorry for this. Here, this, what is this voltage over here? This is V in. Okay. So how can we write the V in versus, V in upon Vs? So V in will be given by Ri divided by Ri plus Rsig into Vs, into Vs. So V in upon Vs will be Ri divided by Ri plus Rsig. Okay, that is very, very clear, right? V in upon Vs will be Ri divided by Ri plus Rsig. Okay, now that means what is my system over here which I am representing? This is the system which I am talking about. Okay, for this system we have to calculate Ri over here. Okay, fine. Same technique which we apply. As you can see here, we have R1 parallel to R2, right? That will be in parallel to R pi plus Re parallel to RL, right? But here the current will be flowing is IB, and here the current flowing into the emitter terminal is IE. So IE will be given by 1 plus beta times IB. So how can we write the formula for Ri now? So Ri can be written as, let me take the color of the pen as black. So Ri will be given by R1 parallel to R2 parallel to R pi plus 1 plus beta times Re parallel to RL. Okay, so that's the value of Ri which we get over here. Fine. So I guess we have found out this Ri value before for I think FL of CC1 or CC2. So let us check it out. No, for FL of CC1 we have calculated, I guess. Yes. So for FL of CC1, the value of Ri is coming out to be 14.98. So we'll substitute the value of Ri as 14.98. Okay. So let's calculate Ri value as 14.98. So let me write the value over here. Ri is equal to 14.98. Ri value is 14.98. Okay. Next is we will calculate the value of V in upon Vs. Okay. So V in upon Vs can be easily calculated now. So V in will be given by, and V in upon Vs will be given by Ri, which is 14.98 K divided by 14.98 K plus Rsig. Rsig value was 1 kilo ohm. So if you calculate that in your calculator, you will get it as 0.937. So that's the value of V in upon Vs. Okay. So finally, we have to calculate V out upon V in. So what's the value of V out upon V in? So let's calculate that now. So basically, if you see carefully, Re parallel to RL. Okay. So we will have to look out for what's the value of Re here. So in this numerical, they have given the value of Re as 5K. Okay. So this is 5K parallel to RL value is 2K. And what did we get the value of GM? GM we got the value as, let me check it out, 24 point something. Let us check. Ha, 24.33 milli. So GM value is 24.33. So let us go back to the calculation. Yeah. So here the value of GM is 24.33 milli, and Re parallel to RL is 5K parallel to 2K. Okay. So let's calculate this. So V out upon V in will be equal to this numerator. We will have 5K parallel to 2K. That will be, let me check out in the calculator. That will be 1.428K. Okay. Divided by 1 upon 23.33 milli. That will be 41.1 hertz, I mean ohms, and it will be 1.428 because again we have over here Re parallel to RL, that is 1.428. So this fraction will be almost equal to 1, that will be 0.972. Okay, so that's the value of V out upon V in which we get. So now we know the value of V out upon V in and V in upon Vs, we can calculate AV mid, and that's the requirement which we have to fulfill. Okay, so finally we will have AV mid, which will be V out upon V in into V in upon Vs. So V out upon V in value was how much? 0.972, and V in upon Vs value is 0.937. 0.937, and the multiplication of 2 will be 0.911. Okay, so that's the value of AV mid which we get. So AV mid, here also we have. Okay, so if we want to convert into dB, it's not asked, but you can convert it into dB. So AV mid will be given by in dB 20 log to the base 10 0.911, and this answer will come out to be if it is less than 1, then it will be negative, it will be 0.809 dB. So that's the answer for your AV mid, right? So AV mid, they have not asked us dB, they have asked us directly with the help of magnitude only, not the dB one. So AV mid, this is my mid-band voltage gain. So mid-band voltage gain. So with this, we have come to the end of the session, and I guess we have completed the low frequency response for BJT amplifier. So next time, I will write down what we will begin. Next time, next lecture, we'll begin with MOSFET low frequency response. MOSFET amplifier low frequency response. Low frequency response. So I will give you all some numericals to calculate, the various parameters such as lower cutoff frequency and mid-band gain. But until then, you all please calculate those values for BJT parameters for those numericals. Solve them individually with the help of calculator. Practice them, and if you make a mistake, please note down that what went wrong. So please complete your low frequency response of BJT amplifier part if it is pending. Okay, so I think I will stop the recording now.